My work I did with my advisor, Eileen Kramer, Sidekicks and Superheroes, a look into student reasoning about concurrency with threads versus actors. Concurrency is a proven difficult topic in computing education. As more modern systems have utilized concurrency, its concepts have become required or recommended in undergraduate curricula standards. Prior to learning concurrency, computing students are typically educated within a sequential framework. As a result, students may struggle to adapt their mental model of computing to fit concurrency concepts, and instructors are tasked with finding the best pedagogical tools to help students overcome these difficulties. Expected learning outcomes for concurrency involve understanding new terminology such as data races, which involve scenarios that I haven't encountered before. They also are expected to reason about what issues may arise from these scenarios and know how to solve them in multiple paradigms. I want to briefly define what I mean by concurrency. A concurrent program is one that has multiple computations happening at the same time, simultaneously or in an interleaved manner. This may result in additional complexity when multiple processes attempt to read and modify the same data. Now let's look at this from a computing student's perspective. You may be familiar with the peanut butter and jelly metaphor from the CS Unplugged activity set. This activity demonstrates how a task is decomposed into instructions that can be sequenced together into a step-by-step program to produce a PB&J sandwich. Students with experience in sequential programming learning concurrency may feel like they know how to make a PB&J, but are suddenly thrust into managing a fully staffed restaurant kitchen on the busiest night of the year. So how do we as instructors help students? With pedagogical content knowledge, or PCK. PCK is not just knowing the content of a course, but understanding how best to teach its concepts, including ordering of topics, powerful analogies and examples, and an understanding of what makes the learning of specific topics easy or difficult. Coming from a constructivist perspective, we do not believe students come into a class as a blank slate. They arrive with their preconceptions and misconceptions in tow, and these have a powerful impact on our engagement with course topics. Knowledge of how students engage with particular topics can help us develop targeted PCKs that address misconceptions and facilitate learning. Our first research question is, what are common and problematic features in student approaches to solving concurrency-related problems, and how are they represented across the levels of an undergraduate computing program? My prior work was based on my first research question, and we wanted to explore student engagement with concurrency concepts across all levels of an undergraduate computing program. To achieve this, we administered a natural language prompt to students to discuss the possible problems present in a concert ticket booking system and how to solve them. There was no programming involved to allow students of all levels to reason about the prompt, albeit abstractly. Student responses, 15 from each of 4 levels, related to the requirements analysis and design phases of the software development process, and we derived an emergent feature set representing student design approaches to a concurrency problem. We identified a number of features, but we highlight 2 here: timing and speed, and additional complexity. But that left the question about the rest of the software development process. How are these features represented across the phases of requirements analysis, design and specification, implementation, and quality of assurance? That comprises our research question 2. For this work, we focused on both research questions and sought to collect student responses representing later phases in the software development process. We studied students in a special topics course in concurrency in the spring 2019 semester, which contained 2 programming projects used in the study. There were 24 students in the class, and they had the option to work on the projects alone or in pairs. Both projects implemented the party matching problem. The first project used the threads paradigm in Java and required UML diagramming and pseudocode. The second project used the actors paradigm in Scala with Akka. Both projects included questions for students to respond to and reflect on their process. So this work provides insight into student reasoning about concurrency in the specification and implementation phases of the software development process. So let's look at this party matching problem. It involves attendees arriving to a party and attempting to pair with someone and leave with them. Our version has a superhero spin. For example, let's say a sidekick is at a party and decides they want to find a partner and leave. They must wait for an appropriate partner, a superhero, to arrive. An arriving superhero can notify everyone of their attendance, and then available partners may immediately pair and go fight crime. With the threads paradigm, the monitor pattern is applied to the party matching problem looks like this. The active object generates attendees, and the data object manages the party. When they arrive, attendees update the appropriate condition, which is incrementing the count of their role, and notify all. They then immediately try to pair and leave. Once the condition is met, which is a partner is available, they update their condition again, which is decrementing the count of their role. This counts as having left the party. The reactor pattern can similarly be used for the actors paradigm in Scala with Akka. With this message passing paradigm, the active object generates attendees and sends messages to update the conditions and try to pair. If they are unable to pair, the data object sends back a fail message rather than waiting, and the active object keeps trying to pair by sending exit messages again. Once attendees pair, their conditions are updated and they send a succeed message. We performed a mixed qualitative analysis. Since we sought to explore student reasoning in this new domain of specification and implementation, we, as multiple raters, open-coded for emergent features in student programs. Our second qualitative analysis was informed by a feature set derived from the natural language design study. In this context, multiple raters closed-coded the program to see how design features were represented in student implementations. Let's look at the closed coding first. The timing speed feature represents misconceptions about computing speed and the rate of execution. In the design study, students stated that fast enough computers would avoid data races. In contrast, in this implementation study, students often attempted to slow processes down with arbitrary wait times. They appeared to use scheduling and wait calls alongside synchronization logic, such as with await, to impose a global rate of execution. The assumption of a global rate of execution has been discussed in prior work, and our findings also indicate the presence of this misconception. The additional complexity feature is realized in student implementations with multiple extraneous conditions, blocks, and Booleans. This was more prevalent in threads than in actor solutions. Each addition can make the already complex task of tracing and debugging concurrent programs even more complicated and overwhelming. In the process of open coding student programs, we found two key features. One is the asymmetry present synchronization and conditional logic. Some students would implement a wait call without including a signal or a notify call in the class. One submission placed in a wait call right after an explicit lock, making it redundant. And the synchronization logic was all clustered within the single function arrive, rather than distributed across the methods of the shared data class. At a slightly higher level of abstraction, students also deviated from the design patterns demonstrated in class by not separating the programming logic between the shared data object and the active object. This example shows synchronization logic used within the active object class, which should not be responsible for the access control of the shared data. The reflections that students provided were also very insightful. When required to provide UML diagramming in pseudocode, almost half of students stated these components were the most challenging aspect of the project. Further, students stated that they did not complete these modeling activities prior to coding, but rather they often completed them after they finished coding and retrofit the models to fit their current implementation. Lastly, we found the students were welcoming of learning new paradigms and frameworks in which to learn concurrency. A helical approach in which the same program is implemented within different paradigms may help students reinforce concurrency concepts and attain established learning outcomes. Regarding threads versus actors, students were very receptive to the actors paradigm. There was less introduction of additional complexity. The projects were sequenced such that threads paradigms were first introduced the party matching problem, and the same problem was used again with the new actors paradigm. Between the two projects, performance didn't vary much. As for implications for PCK, we found students didn't diligently apply the design patterns presented in class. They did not keep shared data logic and active object logic separate, and further, they often clustered synchronization calls within a single function. An instructor may choose to present solutions in class that represent the good, the bad, and the ugly to demonstrate the structure of correct and efficient solutions. The instructor might also consider peer assessment using the similar criteria such as the design patterns to form a rubric. Additional complexity was a feature persistent in design and implementation phases as well. To further address the additional complexity students introduced, program simplicity could be added to the rubric. And finally, students' lack of motivation to perform modeling tasks is very interesting to me. They were particularly resistant to learning strict syntax and modeling prior to coding. My future work is based on this question of what do students' software development processes really look like, and what kind of informal modeling do they perform? Learning more about how students model when unprompted may help instructors realize how receptive students actually are to modeling activities and what kind of work should be performed to incentivize them to model.